Challenge problem number 5. Basically, the first thing that I did in challenge problem number 5 was to kind of lay it out visually. So I drew the problem that it asks in part 1, which is basically to find the electric potential due to a dipole that's set at the origin. So I found some arbitrary point. It could have been in any quadrant, but I chose it here, and there's this distance x and distance y away from the origin, and you have a dipole with q minus and q plus representing the negative and the positive charges of the dipole. And the distance between the arbitrary point and q minus is r2, and the distance between q plus and the arbitrary point is r1. So I just thought it would be easier to label everything so that we could keep things straight. So the first step was to find R1 and R2, and it's pretty simple. You just use geometry. It's actually the Pythagorean theorem. And R1 is equal to the radical of x plus 1/2 s squared, because this is x, and this is just 1/2 of the distance s, which is the distance between the positive and the negative charges of the dipole. And R2 is equal to x minus 1/2 s squared. So that was pretty simple, and once we found those two things, then you can find the potential, because we know that the potential is equal to kq over r, and then all you have to do is just plug the derived expressions that we found for r1 and r2 into r, and then you get this value down here. Actually, you can pull out the kq because it's just constant, so you get v equals, or the electric potential equals kq multiplied by the quantity of r1 and r2. So that is how you do that. And part 2, it was pretty simple to do part 2 once you were done with part 1, because part 2 only asks you to find an expression for the electric field due to the dipole at some arbitrary point. So once you have V, it's pretty simple to convert it to the electric field vector. So V equals kq over r, we know, and the electric field equals kq over r squared. So these are pretty similar equations. They only differ by 1 over r, and we know that E is equal to V times 1 over r. So really, all we needed to do was multiply the expression that we got for the electric potential by 1 over radius. And we know that the actual radius, which is just r on the last page, was just using the Pythagorean theorem, the square root of x squared plus y squared, because that's the center of the dipole to that arbitrary point. So, laying it all out, its electric field is equal to kq multiplied by the quantity of 1 over, and then you have r squared and r1 and r2. Not r squared, but the distance r1 and r2, and then you have 1 over r. So that's how you lay that out. Okay, so part 3 was a little bit trickier, but basically what we had to do in part 3 was use the information from the previous parts to write an expression in binomial approximation so that we could simplify it down. And it's talking about having a point on the x-axis that's really, really far away from the dipole. So it says that x, the distance x, is much, much greater than the distance s. And remember that the distance s is the point between negative q and positive q, and x is the point that's really far away. So we needed to kind of rearrange the equation, the expression, so that we could use binomial approximation to come up with an expression for the electric field of x if it was very, very far away from the dipole. So basically, it took a few tries, but what I started doing was using the information that we had at the beginning, or using kind of the first information that we found. So we know that the expression for the electric field is kq multiplied by 1 divided by x minus s over 2, quantity squared, and then plus, which is we found earlier. And then in order to get a common denominator, we can just cross multiply these two things. So it simplifies down to E equals kq, and then there's this. And then you can actually just expand the top here, and then you can see down here a lot of things cancel out, which is really nice because you're left with just 2xs on top. So next page, it looks like this. So E equals KQ 2XS over this value here. So it's really nice because we can just factor out again. Then you have E equals KQ 2XS over 1 x minus s over 2 to the quantity squared, x plus s over 2 to the quantity squared. So, okay, now the next part was actually really interesting because you're basically just multiplying by 1, but you're adding an x into, you're multiplying this little s over 2 by x over x, so you have x minus x times s over 2 times x, and x plus x times x over 2 times x. So that enables you to, well, as I'm doing down here, factor out an x, but it also means that you can factor out an x from this entire quotient completely, which I do in the bottom. So yeah, you can rewrite this as E equals KQ2XS over x to the fourth, because remember that this x is squared multiplied by this x is squared, and when exponents are multiplied, they are additive, so this is x to the fourth. And then multiplied by the quantity 1 over, and then this is similar to what we had earlier, 1 minus, oh, except for the x value is gone. It's just 1 minus s over 2x squared, and then 1 plus x over 2x squared. So we're nearing our binomial approximation, which we were trying to find, which is 1 plus x to the n is basically equal to 1 minus nx. So that's the goal that we're trying to get this towards, so that we can use binomial approximation. Okay, so we basically reduce this, and we can reduce it even more to get rid of this quotient altogether, because 1 over something squared is just equal to the negative exponent. So we can rewrite this, and then we just cancel an x here. But we can rewrite this as 2kqs over x cubed multiplied by the quantity 1 minus s over 2x to the negative 2 multiplied by 1 plus s over 2x to the negative 2. Now we are ready to use binomial approximation because it matches, oh, I have it written right here, because it matches this, or it's reminiscent of this, it's in the same form. So 1 plus x to the n, this is 1, well it's minus, but that doesn't really matter. X to the n, negative 2 is our n. So, okay, so I did it right here, so 1 plus negative s over 2x to the negative 2 equals 1 minus 2 negative s to the 2x, which simplifies down to 1 plus s over x, and then you have 1 plus s over 2x minus 2, which simplifies to 1 minus s over x. So this is actually really neat that you can use this approximation to simplify something that was a really big thing that was pretty ugly to something that was really simple and nice. Then you can further simplify, actually, and it's pretty easy from this point, because it's just 1 minus s over x, 1 plus s over x. You can just multiply these two things together and get 1 squared minus s squared over x squared. So this is where it gets really neat, actually, because x is so much in this problem, because x is so much bigger than s, because this arbitrary point we're picking on the x-axis is so far away from the dipole, this x squared over x squared can just go to 0, because if you get farther enough away, that dipole looks closer and closer. The distance, that s distance, is looking closer and closer and closer to 0. It basically goes to 0. And so if you let this value become 0, 1 squared is obviously just multiplied by 1, so you can forget about it. And then you're left with 2kqs over x cubed. So we're almost at the end here, and we know that qs is actually equal to p, so we can, okay, so this is the end. So E equals 2kp over x cubed. And that's really neat, actually, because this value right here is exactly what the book had in chapter, I think it was 26, chapter 26, for the electric field due to a dipole. And it was really neat that we could find that using this method. And it reduced all the way down to this value. So that's how you find that.